we have a very small statistical sample that is given by a certain number of observations that you see here on your screen in red. It's 1, 0, 2, 1, 1, 0, 1, 0, 0. These are daily absolute price variations of a given object. Now, what we want to estimate are the empirical mean and the empirical variance. Then we want to get an unbiased estimator of the variance. And the third question is, assume that I can tell you that for whatever reasons, these data, so 1, 0, 2, 1, 1, 0, 1, 0, 0, are generated by a binomial distribution of parameters 2 and p. The question is, if I have the empirical mean, how can I get an educated guess about the quantity p? Now, let's see how we can solve these exercises using our results. Okay, now, if I want to consider the sample mean, this is something trivial. So, as usual, I like to give some basic details because there are basic things that need to be clear before building up more complicated things. If you don't know how to estimate the sample mean, it makes no sense to deal with generalized estimating equations. So it's always very important to be very familiar with the basics. So if I want to compute the sample mean, this sample mean is obtained as 1 over n, the sum of my observations. So in my case, if I consider the sample in red that we were considering, this sample contains 9 observations. So the sample mean is 1 over 9 multiplying the sum of the observations. So 1 plus 0 plus 2 plus blah, blah, blah. If I sum these observations, I get a 6. 6 divided by 9 is 2 over 3. Okay, so this is the sample mean. Now, if I want to get the sample variance, and initially I'm not interested in an estimator that is unbiased and consistent, so I want just to compute the sample variance, what do? I take 1 over n, the sum of the square distances of each observations from the sample mean. So it's 1 over n, the sum of xi minus x bar squared. So if I compute this, this is equal to 1 over 9, and then 1 minus 2 over 3 squared plus 0 minus 2 over 3 squared plus until the last observation, which is again 0 minus 2 over 3 squared. If I perform this computation, the result I get is 4 over 9. Now, what I know is that the sample mean is an unbiased estimator of the population mean, so there is nothing that I have to do. But if I take the variance, what we know is that the variance is consistent but not unbiased. So if I want to get an unbiased estimator of the variance, I have in principle to recompute everything, multiplying my sum of the squared by 1 over n minus 1. Now, this can be done from scratch, so I can recompute everything as I did before, but instead of dividing by 1 over n, I divide by 1 over n minus 1. Or, since I already have the variance, I just multiply everything by n divided n minus 1. If I do that, this number is 9 over 8. And if I apply 9 over 8 to 4 over 9, that is my sample variance, just consistent but not unbiased, I get an unbiased and consistent measure of variability, which is 1 over 2. So my unbiased variance from the sample is 1 over 2 when we consider the sample correction. Now you see that if we take n going towards infinity, so if we have a very, very large sample, n divided n minus 1 is essentially 1, and so the correction is no longer so relevant. And this is the sign that the variance in any case is consistent. So in the limit, the probability of observing a value which is far away from the true value is essentially 0. I have this p-lim convergence. Now, the third question was a question that was asking us to see what we can do from the sample if we know that the observations are coming from a binomial distribution of parameters 2 and b, okay? Now, a binomial distribution is very important. I never like to say the most important, but definitely it's one of the most important distributions in the discrete case. So in a sense, the binomial distribution plays the role of the normal distribution for the continuous random variables. More or less, the binomial distribution plays the same role. And it's a distribution that has a probability mass function as the one that you see on your screen. So the binomial coefficient n over k, p to the power k, 1 minus p to the power n minus k, where n is the number of trials that we have, and p is the probability of success in every trial. Remember that, in a sense, the binomial is nothing more than the distribution that counts the number of successes in a certain number of Bernoulli trials. So a binomial can be constructed, for example, by tossing several times independently the same coin and then looking for the number of heads or for the number of tails. Or if you have an urn process, I can have whatever type of urn with balls of different colors. And then I'm just interested in picking red balls. And so I have the probability of picking a red ball from the total number of balls in the urns. I do that every time with replacement, and what I get is a binomial random variable. Now, if you recall the binomial random variable, you know that the mean of our binomial random variable is n times p. Now, n is the number of Bernoulli trials and p is the probability of success. The point is that in our text of the problem, n is given. So we know that our our binomial is a binomial 2p. So it means that the mean np becomes just 2 times p. Now, a way of estimating p is in statistics, for example, to use the so-called method of moments, MOM. The method of moments is the method for which, if the moments of your distributions are correctly defined, and for the binomial distribution, there is no problem. For other distributions, it can be that we cannot use this method. So think, for example, of a Pareto distribution or a Cauchy distribution are distributions for which, in principle, some of the moments can be not finite. So they are not completely defined. So obviously, in that situation, we cannot use the method of moments. So in the method of moments, what do? We just equate the theoretical moments of our distribution, that for us is 2 times p, with the sample moment that we have computed. So the theoretical mean for us is 2p. The sample mean, as we have computed from the previous slide, is 2 over 3. So what I have to do is 2p equal to 2 over 3. This is the method of moments, equating the theoretical and empirical moments. If I do that and I solve for p, what I get is p equal to 1/3. So I have essentially that looking at this data, I can estimate my binomial to be a binomial 2 1/3.